שנמצא לנו בנושא, אבל אין לנו. כן. ואז אומר, אוקיי, שאנחנו נוכחנו למה שאנחנו חוזרים שלו. אז מה שאתה אומר, זה שכל אחד מהרעיון איך שלחנו, משהו בין 0 ל-1. בין 0 ל-1, ה-CDF הוא לא סתם ערך, זה 1.5, זה 1 ועוד, 1 פחות בערך, ובתוך הערך זה גם 1 וקשר. אני מניחה ששאלתי למה זה ה-CDF, הוא מבוצע ב-FBI, ואז אני רואה שאת לא התשובה. אני לא יודעת, אני לא יודעת. לא על הקשת. אנחנו לא ממש מכפילים את זה בכל זמן, נכון? אז נראה לי שהיה...
Okay, some people do brain research a bit. We are now what is called a finished stretch. There are not that many lectures, and we now start negotiating. Namely, I cannot give you all the material, and there are such extremes that I can give you like more quantum information or black hole entropy, or I can give you more of biology, or engineering. So we need to now kind of negotiate. There is also an option that I can give some material as a special tutorial, because generally tutorials are optional, right? So I didn't mean to make tutorial every week, as long as you have questions about solutions, etc. But as long as there are like few people come for tutorials, I don't kind of want to waste my time. But I can give you tutorial on special subjects, okay? If this is an option. So what I now want to discuss is that I can give you tomorrow a tutorial on particular brain research subject, which is called active inference, which I'm not going to include into lecture. Okay? It's in the book. It's very difficult reading. It's a very short explanation of even more difficult reading, which is the Carl Frickson book on the free energy approach to brain perception. But if you are interested in it, and it means that at least, I don't know, like 5 people or 7 people say that, okay, we'll come tomorrow. Then I'll give it to you tomorrow. Okay? How many people want to come and hear? Okay. It's about perception. What actually happens when you see me? Okay? And to what extent this is, it's very speculative, and it's still not something which is, but it's interesting, and it's relatively modern, and it's something which is very actively now studied. So tomorrow tutorial will be a special lecture on active inference and free energy, but also I want to illustrate some mathematical tricks which are related to what is on today's lecture. So in a sense, it is the tutorial. I write a long formula, right? This will be long formula all the way. Okay? Good. So now, because some people weren't here in the last lecture, as usual, I give you a brief recount of the previous episodes of our series. And as usual, these are very simply about rates. Mostly what we're talking about rates. So before we had one most important formula, and that was formula S, sum of pi log pi's. And the meaning of this formula was that whatever probability of n sequence was decreasing exponentially with n, and S was the rate. That was the main kind of meaning of this formula. This is the rate. Also, but looking from the other perspective, you can say that this is the rate with which you transfer information. So this n sequence is some kind of symbols or object or results of measurements, and this probability distribution of different values here give you the rate with which you obtain information. That was the 0 step, and then we say, well, but there is also another quantity which is kind of also p log p, but it's a little bit different. That was about p of x, y, and the sum was over all x and y, and the logarithm was p of x, y, p of x, p of y. That was called mutual information. That was the second most important formula in this course. And it gave you this feeling that if you, for example, measure x and you want to know something about y, or vice versa, even though these probabilities could be in vastly different spaces, this is the rate with which you obtain this information. And in particularly, if you are interested in the rate with which you transfer information. For error-free, the rate was entropy. This is the rate of transferring. What we discovered is that if what you receive is y, and you want information about x, then this rate must be less, well, generally less or equal, but if you want error, asymptotical error-free transmission, then the capacity, which is the maximum of I. So again, this formula was about a rate of asymptotically error-free transmission, and the formula which appears was p log p divided by essentially what was here is a product, which means that independence. And also this I, a universal measure of correlation between x and y for any distribution. So what was on the last lecture, which some of you missed, was last and final generalization. There will be no more generalization. So the last formula which appears, and this was end. This was the end of information theory. Now we're doing applications from today on. And this formula was when what is standing here, any hypothesis. So this is a formula which measure, in a sense, difference, but it's not a distance in the vector space of distribution. It's a very asymmetric function, and it's a sum of p log, again, pi's or whatever, pi over qi. It's called Kullback-Leibler divergence. It's also called relative entropy, and it sometimes has different names, and it appears like everywhere. So these three formulas are what I want you to remember from this course, I mean, like at a 0 step. Again, this formula, this d is a rate. Rate of what? Again, it tells you that if you measure probability of a given n sequence and you estimate this probability assuming that the probability distribution of any symbol, so you have the symbols, again, symbols are y to n, but each symbol can go up to yd, or sometimes we call it n. So there is like d possible values of it. Could be alphabet, that could be 20 something, could be binary codes, and it will be 0 and 1, etc. So essentially, what it tells you that you have some hypothesis about this vector, d vector of probabilities, and this hypothesis is q. Now you look at your stream of data and you estimate its probability according to this hypothesis, and this probability would behave asymptotically at large n as n times d. So d is the rate by which you invalidate incorrect hypotheses. If you would get a correct, this p, this d would be 0, and on this level this would be constant. So the moment you see that according to your assumption is Q, and the probability of a given sequence of your data goes to 0, then you put some kind of a threshold and say, okay, I consider my hypothesis invalidated the moment its probability of the data is less than some threshold, and this D tells you how many experiments you need to plan if you want to reach this thing, etc. It also, we discussed many different uses at last, and those who are absent can look in the book or can look in the video. But essentially, when you see now, you see that mutual information is a particular case of relative entropy. Okay? And then again, you can say that entropy is self-information, is mutual self-information about itself. Okay? That's it. End of story. From now on, we do applications of this stuff. Okay? No new ideas, well, just applications. Smart applications are also ideas. Any questions here? Good. So we are good. There are three. Everything is three. I mean, redundancy of language is three. Redundancy of there's Trinity in Christianity. There is everything is counts to three. So what we start now is from something a little bit more sophisticated and difficult problems than this. If you have a stream of data, you read probabilities, whatever Q's you hypothesize, just by counting how many yi in this sequence, how many y2 in this sequence. But very often, and in physics and biology, and even in social sciences, you don't get the data, you get averages. For example, let's say that now I would call it x. I'm interested in the probability of x, but the data that I obtain are some sum over x, p of x, rj of x. And those are just numbers, rj's. Okay? For example, you do a scattering of X-ray or neutrons or whatever, and you get some kind of an average position of impurity per wavelength. We'll solve this problem later today. Or you look at your gene expression somewhere, and you get data from many cells. This is an average, right? You could be interested in this probability. So now you are given this set of number, and J could run again from 1 to K. X has again different values. I use D because it's a standard notation in quantum information, so I just don't want to switch. So what was N before, it's now D, dimensionality of my alphabet. The question to you: what is the best P which satisfies these conditions? It's an empirical problem, right? So you're a natural scientist, right? And you get some averages. Apparently, it must be P of X and of all R's, right? With respect to X, it must be a vector which is normalized. Sum over all values of X is unity. And somehow depends on R. How? R's, again, you know this function. This could be X or X squared or cosine X. Some functions of X. Okay? So apparently your probability must be expressed through these functions, right? And these values. How? We already solved this problem once for a very particular case when our R was energy.
Repeat the definition of R and J. Sorry.
R is any function of X.
And J?
J is a number, integer, which runs from 1 to K. So
R is known, capital R?
This is known and this is known. This is your result of your measurement, and you know what you measure. For example, you measure an average X, then R is a linear function of X. Okay? We did it before on a very particular case when we say what we know that the sum of pi, ei, and E is some very special function of I. It's an energy of a state number I. Okay? So I have d states, and for every state I know what is its energy. So I say, this is given. Find me p i's. We solved this problem many lectures ago. How we did solve this problem?
Lagrange multipliers.
We use the method of Lagrange multipliers. You remember? We say, look, what I need to do, I need to find extremum of what?
Entropy.
Why? The right answer, but why?
Because this was the stable state. The stable.
There's nothing about stability. I mean, look, what I'm doing, I'm trying to find the probability distribution which satisfies my condition which I found. This I measured this, right? Now I want to find the best distribution which corresponds to this measure. The problem, there are infinitely many distributions which would have this mean value, right? I can reshuffle probabilities in many, many ways. So I make this statement, which I already did, and so let me make it again. I say that my probability must contain the truth, which means it must give this condition, and you remember? You forgot. And the whole truth. What does it mean, the whole truth? This data. And nothing but the truth. And this is the most important part. Not only in the court of law, right? What does it mean, nothing but the truth?
Maximal entropy.
Means maximal entropy. Which means that you don't assume anything else. Which means that you maximize your missing information, right? Maximal entropy means, well, technically it means that you open your possibilities for further data. But it also means nothing but the truth. This literally means maximal entropy. No hidden assumption, no implicit assumption, nothing else. Which means that now what you need to do, you need to look for this guy, right? So you're looking, but you're looking at it under this condition. So you have a vector space of pi's. It's a d-dimensional space. That's why I call it D, right? So it's a d-dimensional space. And in this space, this condition defines what? It's one condition on D numbers. These are given, right? What it defines in your d-dimensional space, this one condition?
It's a manifold.
A surface. It defines a manifold. Well, it's generally it's smooth, so you can call it manifold. But we aren't in this mathematical stuff. It defines a surface. So now it's a very interesting condition. You not only need to find the maximum. We know what is the maximum without this condition. All pi's are 1 over d. That's the maximum of entropy, right? But now we impose a condition. The condition means that you look for the maximum on this surface, right? On this surface, this stays constant, right? Which means that if you look for a gradient of this E, of this functional, it must be parallel to the gradient of your entropy. Entropy has a maximum on the surface, which means that along the surface the gradient must be parallel to it, because this does not change along the surface. So what Lagrange invented is a very smart idea. You see, instead of looking for the maximum of S, which is a functional of all pi's, I will be looking for a functional which depends on one more variable, right? We discussed it. I'm just doing it again because this is really important thing. You take something which be a functional of all all pi's and some lambda. well, in this particular case, we call it beta, but let me call it lambda. Okay? So what you do, you take S plus lambda E, which is minus P log P ice minus plus lambda sum over P ice E ice. And now this functional, let's call it L as a function of P and lambda, you look for its unconditional function, a conditional maximum. Okay? Namely, well, it's, you do it like this, right? So you put this condition, namely that this must be 0 times lambda. So now, when you look at extremum of this with respect to lambda, you need to differentiate it with respect to lambda and require that the derivative is 0. I did all this. I'm not telling you anything new, right? So when you differentiate with respect to lambda, it gives you this condition. Here it is. Now, when you differentiate it with respect to p, any pg, it gives you, derivative of this would give you minus logarithm of pi minus 1 plus lambda a equal to 0. And the solution of this is Gibbs distribution where z is just a normalization factor sum over minus ai beta, and beta is related to lambda by the condition that d logarithm z over d lambda equal, again, z is a functional of beta equal to this mean image. Okay, so the whole idea is that instead, and it's a very beautiful geometrical idea, right? So instead of looking in the d-dimensional space on the maximum on a surface, you go to the d plus 1 dimensional space and you look for the unconditional extremum, but now with more parameters. Okay, good. Let's go back to our, so Gibbs distribution is just a particular case when what is given your average quantity. But now we have different R's quantities, and we ask what is the probability distribution. So can you tell me immediately what is the probability distribution which satisfies all these conditions and nothing but these conditions?
Saying e to the minus r.
Which are?
Rj of x.
All of them.
Only this x.
Yeah, this is a given x. But for every x, I have different, I have k functions.
I understand.
Okay? So what you need to do, you need to say that now I would have my s plus sum over j from 1 to k lambda j, which I need to find. It's called also Lagrange method of indeterminate coefficients. So these are determined yet. What stands here is rj of x minus rj p of x. Or you can put p of x here because this is just a number and this is... Anyway, so this is your functional, right? And now differentiate it with respect to any lambda, give you this condition, which is then automatically satisfied. Differentiate again, s is still p log p. So again, this differentiating kit would give you logarithm of p of x minus 1 plus lambda rj of x sum over j from 1 to k, which immediately gives you generalization of a Gibbs formula. Those are explicit function of x that you know, that what you measure, right? Now this you don't know. You know this, right? So you need to solve now a system of simple. It's 1 over z, which is a function of lambda i's. Again, by definition, z by definition is the normalization factor, is a sum over j from 1 to k exponent minus lambda j rj of x. It's it's sum over it's sum over x. Okay. So and this is sum over j. So when you sum this over all x, it must give you unity. So z is just a sum of this exponent over all values of x. Right? This is just a normalization factor. Now, if you look at this formula for z, from here you can differentiate it logarithm of z like you did it for Gibbs with respect to lambda I. So what you would find from here, you would get a sum over x, rj of x, and then you would get it 1 over z because it's a logarithm of z, and then exponent minus sum over lambda j rj of x. But this is your probability distribution. So this is just rj of x, p of x, sum over x, which is ri, rj. Okay? So this set of equations, k of them for every j, is an algebraic system which allows you to express lambda through r. And that could be ugly. But still, this is just already algebra. Okay? That's the whole method. Okay? Any question? You learned it somewhere. Don't? Yes.
Can you repeat again what exactly do you measure?
Okay. So what I measure or obtain or somebody given me, this is given. So I know these functions, okay? And these functions are known, and these numbers are known. But what I know is that these numbers are the sum of this function with a known function of probability distribution. I know that they are averages, and I know that the p of x, sum over x, is equal to unity. You can consider integral. I intentionally keep x and j like different notations, right? This is my probability space, those my measurements. I did k measurements or received k sets, okay? Good. And now I'm asking, what is the best p of x here, which corresponds to this data? And my answer is that my p of x must be true, must contain the whole truth, namely all this data. Okay, when I take this probability distribution and sum with this known function, I will get these known numbers. But it also must contain nothing but the truth, which means maximum of entropy. So what I did Lagrange method of indefinite multipliers. I created a functional of all x's and k unknown constants. In this expanded space, I am looking now for a maximum. Okay? I'm not actually solving the derivative of lambda. They just automatically enforce. The moment this is a maximum, this would be automatically enforced. But when I differentiate with respect to p, for every x I obtain this relation, and its solution is this formula, which is it's an explicit function of x, and z is explicit. Yeah, I already written it here. Okay? Yes.
Just a little typo. Isn't the px in this first line should be inside the parentheses, like times only big R, like big R times?
Yeah. That's what I said. I mean, but this is just a number. This is just a number, and sum over x of this is unity.
Okay.
So okay. I still find hard to believe that this simple framework was invented like 100 years after Boltzmann. So it was already invented when I was a student, and it was still, I was taught that maximum of entropy works only in thermal equilibrium. There's nothing about thermal equilibrium here. Maximum of entropy is a simple idea, nothing but the truth. It's a totally general statement. It was actually understood at 60s, but more or less people started to use it at 70s. And it's a very good lesson here, how something trivial can be, at your face, and that it would take people like, 50 years to understand that this general principle of maximal entropy and the condition of your measurement has nothing to do with thermal equilibrium. This data for physicists could be current. You know that there is a current. Okay, so this is a current. You know the value of a current. You know something. Okay. So let's give some examples. Okay. So the simple example is that it's a very simple case. Your J, your R is only one R, and is a function of x, and its x position. So you know mean value of x. You just measure, and it says it. It's here, in this point, is it this way your mean value, okay? Let me call it R. So it's R. And let me make, okay. So what is the probability distribution? Boltzmann. What is the probability distribution?
Like Gibbs distribution.
Huh?
Like Gibbs distribution. It's the same like we did with the energy.
Give me a formula.
E to the minus R.
No. It's probability function of x. It contains R as a parameter. Tell me how it depends on x. It's P of x. How it depends on x.
It's uniform.
Huh?
It's uniform because it doesn't.
No. It's uniform when there is no condition. When there is no condition, then your probability is uniform. That's the maximum of entropy. Now you have a very special point. That a mean value of x is R. It's like 5. So it cannot be uniform. It must be somehow have maximum around 5, right? Okay. Let's consider it simply. Let's consider it discrete. Okay. So let's say this would be I, and mean value of I, and I'm asking you what is that PI's. So how it depends on I? I is the position. Let's say I just changes from 1 to infinity. Well, you have formula. Okay, so your R of I is I. If you plug it here, what you will get?
Exponent.
Huh?
E minus some lambda II.
As simple as that. Landau used to say, money is in the exponent. Your data is in the exponent. What this simple formula tells you, where is my p? P. Whatever you measure is in the exponent. Sorry, because the derivative of entropy would give you logarithm. So your data are in the exponent. Okay, I always remember it by Landau wording. So my probability distribution is exponent minus lambda I, 1 over z, which depends on lambda or depends on this. Okay. So now
I'm sorry, what is lambda? Because in the first
I don't know what is lambda. I'm going to find it now. It's called method of indeterminate coefficients. Okay, lambda is some function of r, right? To obtain it, I need to use this formula. Where is my formula of d logarithm z? Here. I need to use this formula. Z is a function of lambda. Let me compute it. So z is a function of I exponent minus lambda I, and it's geometric series, and it's 1 minus exponent minus lambda. Is that okay? So I now now I can differentiate this z with respect to lambda, and I would obtain exponent minus lambda equal to r1 plus r, and I can even call it p, and so it will be rho, my probability of I equal to 1 minus p, p in the power I. Or you can say that it's 1 minus p, this is my 1 over z, exponent minus I logarithm p, or p is r1 plus r. Okay? So you see, this is your lambda. It's a logarithm r1 plus r. And I intentionally did it fast so you can have a pleasure to compute it at home, right? Because I really want you to take logarithm. This is my z, take a logarithm of it, differentiate it with respect to lambda, then you obtain this relation. But that's a machinery how it works. Okay? Whatever is measured is in the exponent. Tomorrow on the tutorial, I'll show you how Carl Friston smartly used it in doing some kind of a free energy formalism for human perception, just interpreting the data as if it is an energy. Because the physicists have this built-in thing, whatever is in the exponent, it's an energy. It's because we used to Gibbs. But it's just a particular case, whatever is measured is in the exponent. If what you measure are mean values. Okay? So we have this set of conditions, and all this function would go into your probability distributions in the exponent with unknown factors. And finding this factor is just that you need to use this condition. Questions? Okay? No questions? Like no questions because you don't understand what it's all about, or no questions because it's really trivial?
It's not trivial.
Huh?
It's not trivial.
Still soaking with me.
Well, maybe I'm kind of, first of all, if I'm going too fast, slow me down, right? Because, as I say, I assume that you're totally ignorant, but infinitely smart. Maybe these both statements are wrong, and so you, but I also assume that you learned Lagrange method somewhere, so I'm trying to trigger some value memories. Somebody never heard of Lagrange method of multipliers? Like never. So you heard about it, right? So what now I'm trying to, so let me give you some time so you think what you want to ask.
Can you repeat the condition of how you find the lambdas?
I need to express lambda in terms of r. Okay? So now what I obtain is this distribution. I have an explicit formula for z in terms of lambdas. Okay? So now what I'm using to relate lambdas and r's, I'm using the following formula. If I take a logarithm of z, right, and I differentiate it with respect to lambda, then it would be derivative of z with respect to lambda divided by z itself. Okay, so what I divided by z itself. When I take z and differentiate it with respect to lambda, I get r coming here. Okay, so what now I have? Let me use a different color. This one is my distribution. Okay, so what I have here is r p's and those r's. Okay, so for every j now, you see this is a differentiation with respect to j. Okay, I, because j is inside this sum, and this is I, and this is I, and this is I. Okay, so this solution I obtain when I differentiated this function now with respect to p, so I get log, and when I solve this log, I get exponent. From now on, we'll be doing at every lecture. At every lecture, we get exponent of something as a probability or conditional probability, or a distortion theory, or market strategy. This is a general trick. Okay? It gives, you have some data, you vary entropy plus this data, variation of entropy give you log, data variation over p give you r's, what are actually you measure, what are the mean values of what you obtain. All these things would come into the exponent of your distribution. Okay? That's why people very often, particularly in statistics and in particular what we'll be talking tomorrow, call logarithm of probability energy. Well, it's energy only if you consider a very simple case where what you measured quantity is energy and you're in a thermostat, so you're given a mean energy. Sorry, I erased. More questions? Okay, good. So now, again, today we have a brain day, so I'll give you a work which, a very famous work by now, but people from your department actually did, and it's a probability of neurons to fire. So if nobody here heard anything about neurons, so brain people know what neurons are, and for physicists, I'll tell you a simple thing from the viewpoint of this thing. Neuron is a spin, which means that it has two states. It either fires or it doesn't. Okay? Which means you can characterize it by a binary number, 0 or 1, or you can characterize it by a variable which we call spins. So we say that there are sigma, and there is I, and I goes from 1 to d, and there is that many neurons that you can measure, and people measured hundreds in this famous work, but this could be plus minus 1. If it's plus 1, it fires. If it's minus 1, it doesn't. Now you go and measure. What you can measure? You can measure how often a given neuron fires. Okay? Namely, you just look at your data and you find out the proportion of time, and it would give you a mean value sigma I. I call it somehow. Let me find out. I'll call it. Yeah. And also, I can measure what else? What would you measure? If you simultaneously measure 100 neurons as a function of time, you see this fires, this doesn't, this fires, this does fire, etc. What would you could also measure as a simple thing?
Correlation.
Correlation. You can also measure correlation function sigma I, sigma j, okay? And this would give you a matrix, right? So this give you a d-dimensional vector of these things, and this give you a matrix. Okay. So now what you would like to understand, and at this point we go for the break, what is the probability distribution of sigma I? When I do this figure parenthesis, it means that this sigma 1, sigma d. Okay? Break. And after the break, you'll tell me the answer for this question.
It's half a shot.
אני רק חושבת.
So I know the mean value of sigma, and I know the mean value of sigma I, sigma j.
Okay, so we need two constraints.
Just give me an answer. It's really simple. I mean, that's why sometimes, you know, I really want you to just say something which just looks like more plausible. And so that and this guy would stop asking him all this annoying questions.
Gaussian.
Huh?
Gaussian.
Gaussian distribution, which means that it's an exponent of something which is has linear and quadratic term, right?
Yeah.
So it must be sigma i's here with some unknown factor, let's call it h i's, and sum over jk, some j, jk, sigma j, sigma k. Right? And some z, which depends on, this is some numbers, I mean r i's, and this is r ij's. That's it. It's called Ising model of the brain. It's a work. There are many works now, but the original work, if I'm not mistaken, you should correct me, it was Schneidman, Segev, Berry, and Bialik. And why it's called Ising? Because physicist has a very dynamical model, the system with an energy, again, a system of spins in the external magnetic field. Then the energy is equal to the magnetic field times my sigma. If it looks up along the energy, it increases my energy. If it decreases my energy, if it looks down, it decreases. So this is something which has a sign. And generally the different, and it's sum over all this thing. And it could be that different spins experience different magnetic field, namely that magnetic field also could be different in different parts of my sample. And also sigma I, sigma j means that the spins could interact. They interact usually this, I mean, for biology it's probably unimportant, but for physicists I can remind you that usually nuclear have spins, and this wave function of the spin could overlap, and this overlap produces what is called exchange interaction, because there's usually fermions which are there, and they could repel or attract, and there are some factors which corresponds to this. So this is just an energy. So for a physicist, what is written here is an exponent minus energy divided by temperature. It's an equilibrium distribution of spins having these values of magnetic fields on side, and having this, what is called exchange integrals. It could be positive, negative, which physicists call ferromagnetic, antiferromagnetic. What people in brain research discovered that they are sign definite, which means that the system cannot go into a state where like all neurons fire together like epileptic fit or... Anyway, what I want to stress is the following really simple lesson. What for physicists look like an equilibrium distribution of a system of spins in equilibrium, the same distribution describes for biology something which is very far from equilibrium, because when you're in equilibrium, you are dead, right? So when your brain fires, it's definitely you're out of equilibrium. What is important from this viewpoint that you just measured linear and quadratic function, and this what more or less describes pair interaction of two spins and the behavior of spins in the external magnetic field. Right? And again, whatever you measure is in the exponent. Okay, this is a really simple lesson, and of course, while I'm telling you all this, go and read the paper. It's really very interesting, Because the main interest in this paper is that really measuring pairwise correlation, you can really learn a lot about collective interaction of clusters of neurons, and you can even estimate computing mutual information between spins, namely different correlation between different spins. You can estimate the size of a cluster which more or less corresponds to a coherent behavior. So you can get a lot of insight, and it's a beautiful paper, and now after all this you are ready to read it. Okay? Good. So now last thing before we go forward is that by doing this thing, namely S plus sum lambda I R i's minus R i's P i's and getting the probability distribution P, well, let's call it, P, which is exponent minus sum over lambda r's. What we really checked is that it's an extremum. Namely, we checked only the first derivative, and we made sure that it's 0, right? So by differentiating this functional with respect to P, with respect to lambda, this is just a guarantee that it's extremum. It's not a guarantee that it's a maximum. And we're looking for a maximum of entropy, right? Nothing but the truth. So how to prove that this is really maximum and not minimum? And of course there is a hard way, namely you compute second derivative. And there is a smart way, which means that you use relative entropy. So what I just want to show you, an elegant trick, which shows you how you really can prove that this S of P, of this P, is larger or equal than any other Q, whatever other Q you take, okay, if it's not this. So let's consider Q, but again, what we assume about Q is that at least it satisfies the same condition, namely that the sum over all x, Q of x, Rj of x, would give you Rj, namely the same numbers, okay? So let's now compute. So this is given. So now what I want to get, I want to sum over x q logarithm p. This is my p. So what I will get from here, I will get q sum over, when I take log, I would get here lambda r i's, and I will also get minus logarithm z, right? But then again, this is the same as for p, so what I would get here is the same as minus p log p, which is s of p. Again, let me, what I'm doing very simple thing. I'm saying that if I compute q log p, it's the same as p log p. Because the only thing which matters is that it's already logarithm, and logarithm is the same. So now I can take s of p minus s of q, and s of p is again is the sum over x, is a q log p. Of course, it's p log p, but it's also q log p. And this is minus q log q, and this is, of course, g between q and p, and it's non-negative. Okay? So almost any proof from now on of some kind of non-negativity, it's usually done in terms of relative entropy, and also more sophisticated things, which we probably won't be doing, maybe one episode in quantum information is about all properties of monotonicity, subadditivity, convectivity. They're also done by this. So this is a really very powerful instrument, and this simple example shows it. Questions? Okay, so now in this continuing this thing, what I wanna discuss is what happens when you do more measurement and more measurement and more measurement. As we discussed, you see, for example, by relative entropy, how your probability could go down. But you can ask a somewhat different question, and this is precisely what I already promised you to tell. What happened in this conversation between Szilard and Einstein in Berlin University in 1926, probably 27. They will recall it. So you had some Sx, and if you did some measurement, so you get some R, added some R to your measurements. So generally, you diminish your entropy. Now you have a conditional entropy, and the difference is a mutual information, or you may change it. You may call it a change of mutual information. So, of course, it goes back to Maxwell. It's what I will be discussing now is Maxwell demon. So what I want to try to get it back, and not necessarily to physics, but let's assume that you are talking about a system in which there is some conserved quantity, right? So you're doing measurements, but you know about these measurements, about your system, that it could be characterized by something which we will call energy, paying back to tradition of physicists, but it could be, again, it could be money, it could be some other thing, it could be something related to kind of your matter. It's very often just a matter. Anyway, so there is something which is conserved, and you can characterize your system by an energy, and you can also say that if I can characterize it by an energy, I can also look at its environment. It's not a closed system. And in this environment, I can characterize by the mean value of this energy of this environment. So I just put it all in the scary quotes so that you know that it could be generalized. But for now, let's just talk about simple energy. So we have a system, and this system has its energy, but it also in an environment. And the environment has a temperature. Temperature is essentially something which determines the mean energy. And now what I'm asking, what Maxwell was asking and what Szilard answered, I'm doing measurements now in this situation. Okay? What can I say about this measurement and how this is actually related to this? And you probably know that idea. The question that Maxwell posed was the following thing: that I have a box, and in this box there is one molecule. We'll have two Maxwell experiments, two Maxwell demons. First Maxwell demon it's a very simple. It's actually how Szilard rephrased it in this corridor conversation. Imagine that I know that my molecule is in the right side. It's a result of measurement. What I did. What is this? This is log 2. Well, because they were working in the usual logarithm. There was, in all terms, it was Boltzmann constant times logarithm 2. Okay, times temperature would be change of energy. But because my entropy is a logarithm of a volume, if I divided volume by 2, then my delta entropy, which is my delta E, is just a logarithm of 2, or 1 bit. That's actually how bit appears. Well, the term bit is, Americans did it in Bell Labs, but that was the idea. So now, said Maxwell, what I can do, I can immediately get work out of this knowledge. How would you use this knowledge to get work? You just know it right to left, and you immediately say, oh, I know how to get work.
Put something in the middle.
Well, you can put in the middle, indeed, a wall, and then what?
Push.
Now you can push this wall, and you know in which direction the molecule can push it. So you can attach something to it, you know from which side to attach. So there was some kind of a, Maxwell demon looking into all this and saying, do it like this. Right? So now, what is important, that this box is under the temperature T. Okay? So this molecule will be heating this and pushing it and raising this. Okay? So I immediately get the work. How much work I get out of it? Well, of course, you get this kT logarithm 2 amount of joules, right? This you need Boltzmann constant, but I usually use temperature in energetic units. Okay? So one way to look into it, and again, this was something which was much later neatly formulated like this, that you can, as long as you have energy, temperature, and entropy, you can always define free energy. Again, that was a revelation for people. They used to think that you can define free energy only in thermal equilibrium. Well, not necessarily. As long as you have a probability distribution, you can always compute entropy. As long as you have this probability distribution, exponent minus lambda I Rij sum, you can always define S as a function of Ri's. This is just your entropy. So you can always define F, which is E minus Ts, and as long as you did measurement and you decrease your entropy, you increase your free energy. You remember we discussed why it's called free energy. Is an energy that you're free to use keeping the temperature, or it's energy which you can use and it's less than the total energy because of your ignorance. And as long as your ignorance is less, the work that you can do is more. And it's precisely this work that you did it over here. Okay? And it immediately tells you, because of energy conservation, you can get out of this information the work that to do this measurement, you need to delta I. You need to do work which is no less than this. You cannot get energy for free. So if you did something and get ability to make this work, which is T delta I, and this is how much information you measured, just for the fact that you are in a finite temperature means that it's a finite work of this measure. That was a happy state of, this is clear, right? This is still a first law of thermodynamics. Still, and then it's getting non-trivial when we get to the second law of thermodynamics, and we're now already talking 60. 61, not 26, and Rolf Landauer. So now you may ask questions which people somehow did not ask until 1961, but it's a perpetuum mobile of a second type. How you would do, what is, first law of thermodynamics tells you that you cannot get energy out of nowhere. A second time is a more subtle thing. It tells you you cannot use heat baths to make motions. You can make motions back and forth, namely on that your energy would be not changing, but you would get some kind of a motion which has an informational, which we would now see. But you take energy out of heat baths. But you do take energy of a heat bath over here. How you take it? Why this counts on my walls being at a finite temperature?
Otherwise, this will not move the particle.
Well, first of all, particle, let's say, I look at it, particle moves. Then it hits this wall starts moving. Next time my particle hits a wall and give it some part of its energy. And wall moves away from it. So my particle is reflected with less. It needs to replenish its energy, get it back to the same temperature so that it could do work all the way. Whether it takes this energy, it takes that energy hitting the walls, which has a finite temperature. The simple picture, which somehow Rolf Landauer understood and analyzed and said, what the hell? So let's do it again. So now I pushed it all the way. I do this measurement again, doing this work. Okay, good, I did this work. Then I again push it. So I'm moving this back and forth, using only the thermal energy of my heat bath. this perpetual mobile of a second type. That's why I'm telling you that asking questions is really important. Yeah. These questions that nobody asked for, like, I don't know, 100 years since Maxwell. How would you answer it?
But it's not like you need to replenish energy. It's not perpetual mobilize only if it's like.
Perpetual modeling means that you can just kind of do what, like here. It's essentially the example that you can move it back and forth. You move it up, then you use the energy which you get out of here to do measurement. It would go down. Then you, after you did measurement, you again approach it and it moves up because of this molecule. So what you're using all the time the heat energy of a thermal bath, which you assume is somehow always replenished, namely that the temperature here stays the same, namely it's just heat comes to it. But you can use this potential energy which you get after pushing it all the way, because it's equal to this. You can exactly use it to do measurements. Then it would go down, but you did measurements. So again, you know it right or left, so you put it left and again do work again. What is wrong in this simple picture? There's something wrong with it, right?
This is the work that is required to make a measurement, or
This is the work required to make a measurement.
how did we get it again?
It's, look, if out of this information you can do this work, then by the first law of thermodynamics, you need to spend this work to get this information. This simple idea for which Szilard got his PhD. Like they say, Maxwell died when Szilard PhD thesis, Maxwell demon, not Maxwell. Maxwell demon died when Szilard paper appears, and now it's just a poltergeist which harms our castles. But the next question was, what if you do it in a cycle? It looks like you can do cycle, namely returning system precisely to the same state. And for doing all this back and forth, you use only thermal energy. Is it possible? If it's possible, that means it's just...
But if the work we need to put in this, to invest is greater than this value,
assume that everything is done perfectly without losses. Of course, here we assume that there are no losses.
I mean, if there are no losses, then perpetuum mobile is fine, no?
No,
Why? Because
I'm asking you why. Or if it's possible. That's precisely what Landau asked. Is it really a situation in which you look at the system and the system goes back and forth and returns to the same state, and the only thing that you were using is heat? There were no other thing but heat. Because doing this, you use this heat.
Maybe it can't be reversible because of the entropy change.
If you do it like adiabatically slow, you can assume that there is kind of no... But what is here, which is already drawn here, which I did not take into account? I just look at this picture. The bus, we already take into account, but the bus is this temperature. It means that the walls are always kept. What else is here on this picture?
The box.
The box. That what everything happens inside this box.
Yes.
Why it's called now Landauer formula and Landauer paradox and Landauer. He looked at this picture and he understands that there is one more entity which is already here, which is
the demon.
the demon. Okay. So now you know the answer. Why the hell we need to take demon into account?
Because he also
It's a demon, for God's sake.
invests energy within himself.
He
To
has
think?
the knowledge.
He's not an energetic device. He is an information processing device. That is important here. Okay? So, and because we call it M for Maxwell, so what we really need to say is that when we do measurement, is like what we say, right? We get, it's a mutual information between what and what. The moment you see mutual information, you ask between what and what. between our system, let's call it B box, and measuring device, daemon. That's a mutual information between daemon and device. So when your daemon records the fact that in this first step, the particle was in the right part, it's one bit of information. Next measurement is another bit of information. So what Landau realized, and which now has a pretty big consequences, even though people argue for like 15 years that it's kind of triviality, how it is maybe. He understood that the system changes, that as it goes back and forth, in this memory device, we have a memory which increases. Okay? What it really tells is the following thing, that if you really want to return a system to its previous state, you need to erase memory. So apart from the measurement, you have a work of erasure. And this was something which, people did not used to think in terms of always treating entropy or information on the same. So how much work or rather heat release you need to erase information?
Entropy difference.
It must be temperature times entropy difference. So again, how would you erase information, for example? So you have this box, you have a particle, and now you know that in the right-hand side. How you can erase this information? Okay? So one of the ways that you can erase it, you put this wall, you push it all the way here, and then you pull it back. By doing this, you need to do work against it, and you release heat. And this heat would be exactly this delta, let's say, here I need to add delta F daemon, and this would be exactly how much information is in this daemon.
Why do you need to push it all the way back and then?
Because you want to erase it completely, which means that, no, you need to, okay, and then you can here and there, and then you don't know where it is, right? So this is something which immediately had a consequence for computations. For example, if you are in a computer and you have operations which are logically irreversible, something like XAND, XOR, so this from like two different bits you create one. So you now reduce your possible, what we were doing here, we were reducing phase space. Entropy is a phase space, right? So we're reducing and expanding it back. So what was formulated is the following pretty unexpected statement, that as long as your computer makes a reversible logical operation, and it does it at final temperature, every time it needs to release a T log 2 or T times 1 bit. Okay? And our computers are still 2 orders of magnitude higher than this, but people already did very beautiful measurements. There were several articles in Nature, some 10, then 5 years ago, there was kind of much better measurement. So people were doing measurements like this. So you have an analog of it, is just you create an optical trap, and there is a particle, right? And so at some point, you know that the particle is over here, right? And this particle is this is an electric field, namely that the moment it's here, there is force acting on it, and you can always compute the work which is done. So you can make what they call a protocol, so you can change your laser configuration in a way that it would be like this, and then it would be like this, and then you can return it back to this, but after all this, you already don't know in which part your particle is. And then they were measuring Q, which was an integral over time force acting on this particle times the
velocity of this particle, this is the power, so this is the work done. And so they measured all this Q as a function of how slowly they did this process. And they found out that it would come into the asymptote, and this asymptote was T log 2. This was a direct measurement of Landauer formula, namely that you need to erase information which is 1 bit. You do it in a continuous, very slow process. And as long as you do it fast, this work is large. As long as you do slower, there is a limit. You cannot go slower to this limit. This is something which is, maybe except Maxwell, would be new for people in the 19th century. They believe that if you really go very, very slow, you can make your losses as little as possible. This is your heat release, right? And what you realize at the moment that you have information processing, there is a limit, there is a floor below which you cannot go. If your whatever slow manipulation leads to the eraser of information, then you release some heat. Any erasing information means compressing phase space. Compressing phase space means releasing heat. Okay? So this is really a new way to look at the Maxwell demon. Okay?
Why does the demon needs to erase information? Why can't
No.
it just continue to open?
You can let him keep it, this information, but then you cannot claim that you have a really a perpetual memory because you did not make a cycle. You did not return to the same place. You see, you are working like in a spiral, so you're going somewhere. That's perfectly legitimate. But the moment that you wanna say, I return to the same place, what Landauer said, you wanna return to the same place, erase the memory as well. Okay? And the last thing I want to show you is this in a much more trivial setting, which was essentially original Maxwell setting. Maxwell considered this, okay, let me do it, for getting another trick, namely transferring heat from cold to warm. So now where I want to go, I want to return to the very first lecture, which when we were discussing, it's a very, very general thermodynamics. So if you have a system which contains two parts, 1 and 2, and the only thing it can do is just exchange heat in between these parts, and we were asking, and there is the E1 plus E2 equal to E, and it's fixed. Namely that whatever you have dE1 is minus dE2. And we say that just the very principle of maximal entropy tells you that if you look at ds, and this is ds1 over dE1, dE1, plus ds2 over dE2, dE2, and this is dE2 is minus dE1, right? And this is 1 over temperature. So what we'll get here, we'll get 1 over T1 minus 1 over T2 dE1. And in equilibrium, this must be 0, namely T1 must be equal to T2. Or generally, it must be larger or equal than 0, which tells us the following thing, which we were very happy to get this answer, that again, if you have positive temperatures, then dE1 is positive when this is positive. This is positive when T1 is less than T2, which means that you get energy into the system 1 if it's colder, right? And then Maxwell came and said, look, again, here is this demon, looking at all this. Let's say I have an opening, okay? And what I can now open or close it, depending on the information. And the information that I will get will be the following, that every time I see here the molecule which is slower than average, I keep it closed. And every time I see the molecule which is faster than average, I make it open. This way, you can, at some point, make this system colder than this. But you continue doing this, namely, nothing prevents you from transferring your heat from cold system to cold. How it could correspond, what formula one needs to write so that we can describe this process as well. Definitely this forbids it. But it's a kind of a legitimate, after all, you don't need to be demon, right? You can put your laser and you can really measure molecules, or you can put billiard balls over there.
You need to include the entropy of the measurement device as well?
Absolutely. What was, now we understand that the general formula, of course, is not this. The general formula is this one. Now, what is this mutual information between, let me call it just I, or delta, maybe delta because 1 and 2, right? It's something which appeared because you allowed them to interact, okay? For example, it could be that you had one system and then another system and they were totally non-interacting. Okay. Now you brought them together, you create this wall which allows now for heat, they start being interacting, namely that your change of your mutual information between 1 and 2 is positive. There were 0 mutual information before and some appeared, right? Which means that this is positive, which makes this even stricter condition. Okay? It only allows you now to transfer from hot system to cold a finite amount of energy, which is this information. But now let's look at what Maxwell suggests. At his configuration, mutual information is something which, like when you did this, you already use a mutual information. This was about that coming from 1 towards 2, molecule has higher velocity. It means that you had some information before, and after you use it, it's already irrelevant. Okay? Which means that in this case, this is something which is negative. It was, and then it disappeared. And as long as it's negative, then it's positive here. And so you can now make this negative, and it still will be the inequality. Because the inequality is delta S. And this is, in a sense, a trivial statement that you need to treat when you consider entropic changes, your heat and your information on the same footing. It's just part of the same energy. Okay? Again, as long as you are working with a finer temperature, temperature is a coefficient which turns information or entropy into energy, and other way around. So now what you understand is there is no paradox. You had some information before. After that you used it. So the change of mutual information is negative. So now your condition is this is larger than some positive, this is positive, so it's larger than some negative value. So this could really allow you a negative transfer, namely that this could be negative even when T1 is small. Okay? So you can take from cold and give it to hot. Okay? So this, why I really want you to see to what extent mutual information resolves all these paradoxes of classical statistics. On the previous lecture, we discussed that this Boltzmann, what counted Boltzmann, let me remind you, and this would be the last thing, that Boltzmann was saying that the sum of SI, of particles I, is something which grows. But on the other hand, we know that S of P1 Pn of n particle entropy is conserved, right? And we understand that the difference between them is just a mutual information between particles. So the statement that this, if you start, like Boltzmann deriving his equation, from a state of non-correlated particles, let them collide with each other, then mutual information would grow. And the sum of the entropies would grow, but the total entropy of a system would be conserved. So you can formulate second law of thermodynamics as just a conservation of a total entropy, not as a growth of additive entropy. This is not true entropy. This is true entropy. It's conserved. The moment your correlation grows, this grows as well. And again, here, the same. The mutual information as an idea, as an understanding that you need to ask how much information is this about this, or how much correlation resolves all the paradoxes. No paradoxes. Everything is trivial. Okay? Questions?
Can you again define what exactly I want to?
This is a change of a mutual information under the process which brings DE1 to the system
But again,
E1.
mutual information of what and what?
Mutual information between system 1 and 2. Okay? So if you knew something about molecules going from 1 to 2, this is something about a mutual information between 1 and 2. And it allows you to transfer heat from colder to warmer system. Okay? In this framework, your change of mutual information is positive. You did not have it before, and you have it after, in principle. Okay? Then in this situation, you cannot transfer heat. But in this situation, when you have extra information, and then you use it, then your delta I is negative. That's it. Okay? It's very simple. But it's really important that you, in your formulas now, information and heat just come together. Okay? Good. So tomorrow we'll have this perception, how we actually see each other, 3:15. And again, if you have any questions about problems, then you're welcome to ask them today.
It's tempting, I think, to ask the question, what can be done with like an entropy maximization principle in turbulence? I know people have attempted something, but does it
I
get
don't
anywhere?
know. The main problem there is what condition you need to take. What condition?
I mean, it's not just you say like the power flux is constant. And
Looking
then,
for maximum entropy under the given flux, drop me nowhere. So apparently the problem, and it's actually written in the book, that we don't know what condition to achieve. It's not,
when you say nowhere, what happens?
namely, I cannot derive, for example, a spectrum of weak turbulence out of any entropy maximum. I can derive an equilibrium spectrum religions, but not to this. Which means I don't know what condition to impose to add to entropy maximum. That's the main question.
In black hole, the radiation supposedly emitted from the black hole is that one, or with relation to the temperature difference?
Both. First of all, radiation in a black hole comes out of entanglement between inside and outside. Okay, this whole process is because you have a pair which appears one on one side and another on the other. It's only possible because of quantum entanglement. So in this respect, it comes out of mutual information. But the fact that this one going away takes heat with it, which means that black hole evaporates. And this is another great paradox in information theory. I'll talk about it. Okay?
Thanks. it.